Hello, everybody. Thank you for attending this webinar. My name is Victor Niño. I'm the Director of Business Development at Equinox. Just before we start, I just want to mention that we want to use the questions. So if you have any questions along the webinar, please use the question board. And then I have a couple of questions for you, actually, that you can answer through the chat. So we can start right away. Thank you again for attending this webinar. So let me see. Well, about Build Equinox, we develop solutions for healthy, comfortable, and sustainable lifestyles, learning to live our daily allowance on solar energy. I think you guys know us about the product that we do is the Serve2. It's a smart, we work on products that is smart, healthy air, quality, and comfort. This is the most, right now where we have this and we are developing this as a new operations coming, but there is an exciting pipeline of products, especially in indoor air quality. And one of them that you will hear soon about is in schools, improving the indoor air quality in the schools. Check always our website. There is always a lot of literature, a lot of newsletters about that has tons of results on experimental research and computational analysis on indoor air quality and comfort. So today, the outline of this presentation, we are gonna have a little deeper, basic understanding of the indoor air quality. We're gonna start with the benefits of the fresh air. We are gonna understand what are the type of pollutants and what is the effect of those pollutants that we find indoors on health, and then how we wanna achieve the healthy indoor air quality inside our homes. One is definitely monitoring pollutants. Then we are gonna talk more about what are the type of recommendations we provide for healthy indoor air quality guidelines, and then all the mechanisms that we use to reduce the pollutants inside our homes. We're going to talk later about the smart systems, and then have some at the end of the presentation, sustainability and cost of health, and finish it with a summary. So the first question this is a question for you guys. It's, what are the benefits of breathing clean and fresh air? Why don't you guys use the chat and maybe answer that question, maybe in a couple of words. Maybe the chat is not working, so we continue. If you guys can use the chat for some answers. But basically, there is a reason we like to breathe fresh air. We cleanse our lungs, we provide oxygen to our brain, and in general, it makes us happier. Basically, there is all this, the clean, fresh air that we get into our lungs is there is a lot of benefits. There are benefits on health. There is a lot of research papers, a lot of investigation studies that it makes us feel better, it gives us better, it helps us to think better. So there is a benefits on the cognition side. In the sleep quality, we can sleep better with having good amount of fresh air, and also we can accomplish more. We can have better productivity in our lives. So let's talk about pollutants and the health effects. What is the underlying issue? The issue is that 90% of our time is spent indoors. So at home, we spend about 70%. These are some results of some studies. And in buildings, basically, when we go to work, when we go shopping, we about 20% of our time is basically spent indoors, especially during the winter. And according to the U.S. Environmental Protection Agency, the pollutants indoors are often about 2 to 5 times higher than typical outdoor concentrations. So we are bringing and we are breathing a lot of pollutants inside our homes. So what are the type of indoor pollutants that we can find in our homes? So this is a graph where I'm gonna basically plot all the type of particles. So the axis below is the particle size. So we go from 1,000 microns. 1,000 microns is basically 1 millimeter to basically really small to the molecular level. So just to start with this graph, I'm gonna say what is the size of a human hair. So the diameter of a human hair is about 50 to 70 microns. So we can start with dust. So we have in our homes dust, basically the heavy dust, the setting dust, basically cement dust, and suspended atmospheric dust that it comes basically from construction site, from basically outside, all this dust that it comes here. Then there is this particle contaminants from combustion. We have ash, we have smoke. The smoke, it could be coming from cooking, it coming from basically the exhaust of our cars, but also we're starting to see recently all this wildfire smoke that it could go into our house. Then we have the smoke also from combustion of especially our cars and some industrial processes. If we smoke, there is the tobacco smoke, and then we have the soot. So if we are starting to see, then we're starting to see very microscopic pollutants coming into our house or participating in our house. And then we also have the biological contaminants. Pollens are basically in the largest side of the particle side, the mold spores from mold growth. And then when we start going into like house dust mites, they're starting to go smaller. Everything related to allergens of animals, also pretty small. The bacterial. And then we have the viruses basically in the spectrum of the lowest size, basically particle sizes. So all these things are basically in our house, they potentially being in our house. Now from a gas, so all this, what I just mentioned here is just particles, but then also we have all these gases that they are contaminants. One major one that we're gonna talk a little more in this presentation is about carbon dioxide. Carbon dioxide can come from basically the air, everything that we breathe out, and but also from combustion as well. Carbon dioxide comes from combustion, basically cooking or all the combustion activities inside our house, for example, space heating or water heating. Carbon monoxide, it's a lethal component. It comes from incomplete combustion. We have to be very careful with that gas, as you know. And there is many other gases contaminants that come from combustion. For example, nitride oxide or bioxide, or sulfur oxide. We also have radon that basically comes from Earth. It's a natural component that it's coming from Earth that we should be also watching for. And then ozone, that is basically still unstable component, but it's still, we see that hearing it more often is when there is all these chemical gases reacting with the light of the sun. We also have what we call the volatile organic compounds, that are also basically chemical gases. One of them that they are human generated, so we generate our own volatile organic compounds, but they're also coming from combustion, from building materials, from cleaning products, and from cosmetics. So this is a map of all these potential harmful pollutants that we can find in our own homes. So the effects on the human health, it's, well, it could be annoying, basically just smelling bad odors, but the ones that we don't smell, that they are specifically, they could be harmful, that it could have immediate health threatening. First of all, it could have irritation of eyes, nose, and throat, headache, allergic reaction, asthma. It could provide asthma, contagious diseases, or even it could cause fatal consequences. And we'll explain more how there is going to be also long-term effects, cancer, respiratory diseases, and debilitating well-being. And we know all this, and it depends on concentration levels, exposure time, age, and also health conditions. Let's talk a little bit more about particle deposition in lungs. Basically, yes. So as humans, we have basically a shield that can help us get rid of the gases and contaminants that we breathe. But there are some contaminants that they are, the smaller they are, the deeper it goes into our lungs, the harder it is for us to basically expel or take out from our system. And the smaller they are, they actually can reach until basically the pulmonary alveoli through basically mechanisms of diffusion, and also could reach even the bloodstreams of our bodies. And this exposure to fine particles, well, definitely there is going to be some immediate effects like coughing and wheezing, shortening of breath, and then we could have some asthma attacks, cardiovascular effects, including heart attacks, heart failure, and strokes. And if you are exposed too much, it will be reduced lung development in children. And as I mentioned, all this depends on concentration levels, exposure time, age, and health condition. So how do we reduce all these pollutants concentration indoors? So our recommendation is basically, let's go and solve the root problem. What is the root problem? How are we gonna solve this root problem? First, we're gonna monitor the pollutants. Then we're gonna compare this to a maximum allowed concentration. So we need to understand what are the type of numbers that we need to start using to compare to understand what is a bad concentration, what is basically a healthy concentration. And if those concentrations are higher than this maximum allowed concentration, then we're gonna act. We're gonna try to find mechanisms to reduce these pollutant levels. So let's talk first about monitoring pollutants. So the question is, I think technology has been existing on how to monitor pollutants. The question is, how can we measure affordably in our own house with our own budget? So first, let's start with the gases contaminants. So the first thing that we say is basically, well, let's start measuring or monitoring the ones that the gases that they have immediate health threatening, that they are basically threatening to our health immediately. And the biggest one is basically carbon monoxide. Carbon monoxide. Carbon monoxide comes from incomplete combustion, is very lethal, and basically a small concentration could actually be deadly as well. So we need to have a monitor for that. Monitors are basically accessible, commercially available for carbon monoxide. Also radon, it's a gas that we want to have to keep an eye on, especially because they have long-term effects on our lungs. I think it provides cancer issues. And another one that we like to also monitor is carbon dioxide. And we will see through this presentation all the benefits of monitoring carbon dioxide and keeping it into the healthy levels. Then we also want to, now sensors are becoming more commercially available to monitor all these volatile organic compounds. So we want to also have monitors specifically for volatile organic compounds. The sensors are not kind of like selecting which components, which gases are, but at least we can understand overall a mix, what is the concentration mix and what are the levels there. So these three are more for gases. Now, there is a whole realm of particulate matter. So also, affordably, we can now find some particulate matter sensors that they call the PM10. PM10 basically is that we are measuring particle sizes, basically all these particulates that have particle size of 10 microns and lower. So we can have sensors that they can help us understand and measure all that area. Then also we have the particle matter for 2.5. Basically, all the particles that they are 2.5 microns or lower. And PMs of 1 basically is becoming a little more accurate on measuring the particle sizes, and it can help us to understand what are the type of, the concentration levels at for particles that are smaller. And as I mentioned before, the smaller the particles, it gets deeper into or basically lungs, and those are the ones that we need to also be watching for very closely. So let's talk first about carbon dioxide and volatile organic compounds. If you go to the website or website buildequinox.com and Fresh Air, you're going to find 4 important papers where they explain what is the impact of carbon dioxide and volatile organic compounds on health, cognition, sleep, quality, and productivity. Basically, now that there is more access to monitoring and sensor devices for carbon dioxide and volatile organic compounds, there is an opportunity for researchers to start doing studies and see what are the impact of those levels into these 4 categories: health, cognition, quality, and productivity. So I recommend if you want to learn more deep about these type of topics, go to that website and talk about it. So the first one is basically that there is definitely, if the contaminants are very high, there is a risk of sickness, or the probability of being sick increases. Also, there is a second one that is basically impacting the cognitive function. I have a graph later on about explaining what are the type of cognitive functions that higher concentrations of pollutants can negatively impact. Then we also have sleep quality. Could also be, it could be improved significantly when you start reducing those concentration levels. And also there is the last paper that is more about understanding what are the costs. So sometimes we want to reduce the cost of energy, we want to reduce the cost, but sometimes we implicitly we are actually increasing some of the cost on productivity, cost on health bills, basically visits to going to the doctor. So those are the type of looking at basically everything from a holistic point of view. We want to understand better, and these type of papers can explain this in a very good way. So innovation is making sensors more affordable and more accurate. So one of our biggest recommendations is that every space now should measure carbon dioxide and volatile organic compounds. And the reason is because papers and research is suggesting that there is a big impact on health, cognition, sleep quality, and productivity. And now later on, we're starting to see all these accurate particle sensors that we could measure actually very, very fine particles as low as basically particle sizes as low as 0.1 microns. So those sensors are now more available. I think now let's start to use them to start monitoring the health of our air indoors. So as I mentioned, particle size matters. We discussed basically all the particles. We saw that the smaller the particles, like viruses, the soot, the smoke, they're getting deeper into our lungs. So we want to use basically all these sensors that now they're available, affordable, to try to track those particles and control them. So we want to have mechanisms of control these particles so they are not high. One comment about how to measure these particles, and it has to do with the particle size. So this is just an infographic showing, just imagine the human hair. The human hair, this is the diameter about 50 to 70 microns of diameter. So if I want to compare a particle size of 10 microns, this is how it's going to look like compared to a human hair that is already, the diameter is pretty small and almost not visible from the human eye. So when you start going into smaller particles, you start to see that the particle size is starting to be increasingly, it's very, extremely small. Even the ones that they are like virus size for this infographic, I cannot even plot it. So that's something that we need to take into consideration, because there is some sensors will measure basically the weight of the amount of particulates we have in the air, and some sensors are also including what is the number of particles that basically a particle count in this in the indoor air. So we needed to actually measure both, and the reason is this: for large particles. So this is an example where like particles about 5 micrometers or microns. This is 10 particles in here. They will weigh about 3.5 micrograms per cubic meter for this type of concentration. Let's assume this type of concentration, it will do that. Now, 100,000 particles with a size of 0.1 micrometers, they might weigh just 0.1 micrograms per cubic meter. So if the sensor is measuring just micrograms per cubic meter, basically of all the particulates within your air, then you don't know what's happening with extremely fine particles. There is no visibility of all these extreme particles into that might go into your lungs. So we have basically, our best approach is basically measure both. So we will have to put a sensor that is in the particle mass dominated, a sensor that can measure by weight all the particles that they are large, and then a sensor that measures the smallest particles. And then we have basically use particle counts just to calculate the number of particles per liter in this air. So those are the two sensoring that we recommend we have, and they are available commercially available. So just to summarize, when we want to have a healthy indoor air quality, we want to monitor pollutants constantly. One is carbon dioxide. Basically, there is tons of research showing that carbon dioxide affects health, cognition, sleep quality, and productivity. Volatile organic compounds also have that same effect. And then we are starting to learn now that there is more access to these particulate matter sensors. We also we're suggesting and recommending basically have two types of sensors. One is measuring the weight, that's basically understanding what are the big particles in our air, and then for the smaller particles, we should be measuring is using particle count as well. Some additional considerations: if your home has a few appliances like stoves, furnaces, fireplates, etc., definitely a carbon monoxide sensor should be in place, and then check periodically radon and radon with a radon sensor. All these sensors that I'm providing here, they are commercially available and affordable for us to basically understand our indoor air quality. So now, what is the next step? So now we know how to monitor pollutants. We recommended 4 types of pollutants that we want to basically watch out. And then now we want to have a comparison. What is healthy and what is something that is going to be harmful for our health. So let's talk more about that. So right away, we have we're calling this the Build Equinox Healthy Indoor Air Quality Guidelines. Based on research and experimental results and studies, we want carbon dioxide to be lower than 800 parts per million. That's a number that you maybe have heard many times with previous webinars. We want to maintain that number in there. And later on, I can explain more in detail why. Volatile organic compounds. Basically, we want is to keep the level that is basically associated to the carbon dioxide. So as humans, we are emitting both carbon dioxide and also volatile organic compounds. So we need to find what is the level that it's associated to this 800 ppm. So far from all research, it's about 125 parts per billion of volatile organic compounds. Then the total mass for all particulates, that is basically 10 grams, 10 micrometers, the size of 10 meters and smaller, we want that to be less than 10 micrograms. So we are measuring here is total mass per cubic meter, sorry. And then the total count. So we want to also count the smaller particles, the fine particles that can go and into our lungs. And we have a number, a practical number that is 40,000 particles per liter. So we want using a sensor that is about 0.3, a sensor that captures the 0.3 micrometers size particles. So these are numbers that they are based on literature and experimental research. They are known to improve health. They are practical and achievable. As I mentioned, research shows that reduces sickness, they improve productivity, cognition as well, and it can achieve in an energy efficient manner. Some additional considerations: carbon monoxide. These are all more related to all the agencies provide recommendations. Carbon monoxide has to be lower than 9 parts per million, and radon about 4 picocuries per liter. Again, right now we are focusing on just the maximum allowed, kind of like the recommended guidelines. But exposure time becomes important when higher than those values. The exposure time, we are working on next webinars on focusing more on what is the type of exposure time and what it means. Like what are the type of exposure time that we need to watch when the concentrations are higher than this. So again, regarding carbon dioxide, why we're recommending 800 ppm, these 4 important papers that we're explaining that they're in the website is telling us basically that. It's basically they have found a lot of correlations between the impact, like trying to, if we reduce the levels to lower than 800 ppm, you're starting to see a reduction on sick days, improving of cognition, improving on productivity, improving on sleep quality as well. So those papers are basically the foundation of the recommendation of carbon dioxide to be less than 800 ppm, and of course all the additional research that Build Equinox has done through the years. This is a graph that comes from an Ashford journal. Basically, the impact of carbon dioxide on human decision-making performance. So they really did measure the impact on cognition. If you take a look closely to basically carbon dioxide about 2,500 parts per million, you're starting to see a major degradation of your cognition skills. Basically, it strongly impairs the initiative, information utilization, approach, strategy. And most likely we have been in these type of situations where we are in a crowded space, trying to work, and it's just basically hard to do it. We cannot think well. And that's another consideration when we are now moving towards working at home. So we need to start measuring this type of carbon dioxide, volatile organic compound, just to understand if we have the proper healthy environment also for work as well. Some notes about volatile organic compounds. Today's ventilation standards, they do not specify volatile organic levels. These are all research based on Build Equinox is providing all this research activity and studies to start moving trying to understand a little more these volatile organic compounds. So first, humans produce about 20 milligrams per hour of volatile organic compounds, primarily isoprene, acetone, ethanol, methanol, isopropanol. Both carbon dioxide and VOCs are proportional to metabolism levels. So if we are exercising, the higher the CO2 and the VOCs are going to be. Also the VOCs depend also of basically the things that we eat. There are some chemical reactions inside our bodies that create all these volatile organic compounds. If it's too high, they impairs productivity, degrades sleep, same as carbon dioxide. And the maximum levels the VOC recommended, and this is more studies from basically our own studies, is we are trying to basically associate with the maximum human-generated carbon dioxide. So we know that we increase the carbon dioxide, the VOCs are going to increase from a human standpoint. So we want to also have basically a correlation of those two, and then trying to bring down those. And the reason for that is basically because there are other sources of VOCs. There are VOCs from cooking and gas combustion, from wood combustion. If there are leaks into our furnace or water heaters, those gases could come in. If it's a bad design outlet system or exhaust system, we might bring those gases here inside. And there are also from other places, from cleaning products, from cosmetics, from even new furniture or new carpet, we can get all this. So that's basically, we want to understand what are the VOCs that they come from a human. So that's basically the level that we want to use. So when there are some other VOCs that they come from other sources, we try to bring them down. Notes about particles. And I think you might be familiar with lots of studies that show that cancer, stroke, heart attack, dementia, respiratory problems are reduced when particles are reduced. So unfortunately, no safe limit defined on number of particles. So we need to do more research in that area just to understand more. The Environmental Protection Agency, they recommend based on weight, about 12 to 15 milligrams per cubic meter for PMs of 2.5, basically 2.5 and smaller. We are recommending to measure both total mass and total particle count using a sensor that is PM10 and trying to keep that lower than 10 milligrams per cubic meter. Sorry, this is a little bit more stringent than the levels recommended by the Environmental Protection Agency, and also focusing on particle count. As I mentioned, the finer the particles are, it could reach really, deeper into our lungs. So we want to watch that. And then a practical number that we have for now is 40,000 particles per liter. We're going to put more research on understanding that particular number. So in summary, we have basically four monitoring sensors that we want to use for everyday use, basically every minute, just to watch the concentration levels indoors. And then we have now our indoor air quality guidelines providing some data based on literature and experimental research just to keep them lower than those values to have a healthy indoor environment. Now, I think now we understand, I have explained the best way to solve the root problem or improving indoor air quality is first monitoring, measuring, monitor pollutants. Then we are going to compare those levels, concentration levels. We are now recommending these Build Equinox indoor air quality guidelines with some numbers based on research. And now the next thing is what we're going to do when they are higher. So that's where we want to act. We want to reduce those pollutant levels. And what are the type of mechanisms that we want to use to reduce the pollutant levels? So one is source control. If we know that there is something that is bringing all the source, yeah, basically all the pollutants, we want to try to get rid of it or minimize. We understand ventilation, dilution, basically bringing fresh air inside. We want to have also some mechanism of filtration, basically trying to remove as many particles as we want. And then for some of the biological components, we want to have basically cure those. We want to have microbe deactivation as those. And then there are some filters that they have adsorption. So filters are mostly for particles. There is the adsorption type of mechanism that is basically, there are some components that they can also absorb some gases as part of the filtering system. The most effective system, there is no here competition, there is no one solution to do them all, to do, to guarantee an indoor air quality. We need to basically use them all. So the most effective system is the one that uses them all. So let's talk a little bit more about source control. So source control is restricting the pollutant or contaminant access. So by design, basically, let's say that we want to have the fresh air, the intake, for example, far away from areas that they have chemical reactions or so on. Maintenance is important. For example, keeping the furnace always in a good maintenance cycle, just to make sure that that we are not generating the pollutants due to bad maintenance. And then prohibiting use. The one that is the most common is like no smoking in our homes or other ways to basically prohibiting use. Basically, it's not having that pollutant indoors. There is I think you guys are familiar with building electrification. Basically, it's trying to get all this equipment on that is basically combustion based, like the gas water heater, the furnace for space heating, or the gas stove that are using combustion for generation of heat. We want to move those into kind of like more into the electric side, using heat pumps, the technology, efficient electric technologies, trying to for those appliances to have access to clean energy. That's a way for source control as well. Definitely, we are removing combustion. There is no carbon dioxide. There is no VOC generated. Now we're moving away. So there is a immediate benefit moving to building electrification. Improve safety, because now there is less chance for carbon monoxide leaks, and of course we talk about access to clean electric energy done by renewable energy like solar or ventilation. The purpose of ventilation is to bring outdoor air to dilute indoor contaminants, basically to reduce the concentration. So this works well for gas contaminants and for particles as well. Both particle contaminants, for example, the ones from combustion, and the biological particles. We have everything that I'm saying here is all basic. Every topic we can talk about an hour, and we're actually trying to build this kind of like a webinar series where we're gonna start going in more detail about all these type of things. But air infiltration by itself, it's a big topic. Air infiltration is basically bringing unconditioned air from outside. It's becoming a little in focus is because we want to reduce the infiltration to reduce basically energy losses when and energy bills, for example. So, but unfortunately, this is still part of ventilation. Part of the calculation of ventilation is air infiltration. So it's basically taking into account the air that comes in filtration. Some air it could be good infiltration, sometimes it could be bad, especially when the air that is coming inside is going through areas where there is more growth, or there is some insects or some other sources of contaminants. We also have natural ventilation. Basically, it's opening. We're familiar with opening windows when outside is very nice. Unfortunately, for some areas like Wisconsin, where I live, we cannot do this every year. Through the whole year. So we cannot use it basically through the year. And then we rely on mechanical ventilation, that is basically using fans to bring fresh air to our homes. So as I mentioned, everyone has a very deep, we could talk for hours for each of the topic, and we're gonna develop a webinar series talking specifically on this type. Filtration. Filtration is also another way to get rid of contaminants. Basically, it works for particle contaminants, and biological particles. There is a removal efficiency. The removal efficiency is basically comparing what is the concentration after the filter compared to the concentration that it was before the filter. And I think you guys are more familiar with the MERV. Basically, it's a removal efficiency designation that is the minimum efficiency reporting value. It's a classification from 1 to 16. The 16 is the finer, the more efficient of the filters. They follow a test according to ASHRAE standard 52.2. And I want to have a little bit of a discussion on how a filter works, how we remove the pollutants through a filter. So there are mechanisms to trap the filters. There are ones that they are more kind of like that makes sense, that they are it's basically the impact and interception. So basically, you have a filter, and then the particles want to go through. There are some of them that are going to be impacting the material of the filter, and then some of they're also going to trap through interception as well. So a typical curve of this kind of like impact and interception, it looks like this. It's basically, especially, for example, this is a MERV 12 filter. It's basically 100%. The filter removal efficiency is about 100% for larger particles. When you're starting to become very small particles, then the removal efficiency becomes lower and lower and lower, and especially for small particles, extremely small particles, basically the efficiency is 0. Basically, it's not removing through this effect of impact and interception. So that's how this is a mechanism. It makes sense for us. Basically, yeah, the smaller the particles, and if there is a wall in there, there is less chance for a wall, basically a net to get rid of the smaller particles. One mechanism that is hard to understand a bit is the process of diffusion. Now, this is actually extremely important in the removal efficiency. The efficiency is basically the movement of particles from high to low concentration. And I think you guys have done this experiment. It's basically just put a dye on the water, and then you're gonna see that basically the concentration starts from parts from high concentration, and this process of diffusion is basically it's a movement from high concentration to low concentration, and then you will have that effect. So we actually can see that effect, and some experiments have measured that effect into the filters. So this diffusion, basically the very small particles can, through the process of diffusion, can actually stay in the filter. And if you see the graph, the smaller the particle, the diffusion, the removal effect due to diffusion is higher. So the smaller the particle, the diffusion effect becomes higher. And that's basically, this is a paper based, I have in the reference by Korlasky and Barflet. Basically, they do that measurement and they understand the modeling. So now to understand the real filter removal efficiency is basically the summation of those two mechanisms. One is the impact and interception that for us, it's a little more understood, basically a lot of blocking of the particles. But for the smaller particles, there is this process of diffusion where basically it goes from concentration. So just imagine, well, the filter has to be with no concentration at all. And then when basically the stream has high concentration, that's where the smaller particles will stay in the filter. There are other mechanisms. Another one is basically electrostatic attraction. Basically, if the particles are negatively charged or positively charged, and the filter might be in a different charge configuration, basically attract through electrostatic. So those are the type of removal efficiency. This is the best explanation on how mask, the face masks work. Basically, this diffusion. We're talking about the viruses being so small. There's through diffusion. Those are the ones, and if through the process of diffusion, the particle will stay in your mask. The filter removal efficiency. So these are also from the paper that I explained there in the references. There is the link to this paper. But basically, yes. So the higher the efficiency, so it's basically the two combined. So you could see here going from MERV 6 to MERV 13, the 16. As I mentioned, the 16 has a higher removal efficiency, and you could see for all the filtering, these two basically the summation of those two effects. One, the interception, and the other one is basically the diffusion. As I mentioned, viruses, the soot, all the extremely small particles are basically in the lower range, and that's how, and the filters have some removal efficiency in this lower range as well, due through diffusion. And the ASHRAE Epidemic Task Force recommends basically MERV 13 higher in the latest studies and positioning. That's how they define this. Basically, they saw that through these studies that the higher, yes, this designation higher than 13 have this better removal efficiency for for very small particles. One additional consideration that we need to understand is basically the pressure drop. So we cannot just take one filter and then put a better filter. We might create some issues inside the system. So we need to just watch out for that. Typically, the higher the filter, the more dense, the more packed, it will create higher pressure drop that it might create some problems with the airflow. So sometimes your system could be handling that pressure drop increase, but sometimes might not be achievable. So we need to watch for the pressure drop due to improving the filter capability. Then we finally we have the microbe deactivation. The microbe deactivation is basically we recommend the ultraviolet germicidal irradiation filters. They're typically used in hospitals and laboratories for disinfection, but now they're affordable. They use ultraviolet basically to kill the microorganisms, the biological ones. And then this is an add-on. So, and I explain what are the things that we want to recommend. Basically, an add-on. This will not remove particle contaminants, but they use the ultrawave light just to kill the germs and microbes. It uses and recommendation is also LED lamps. So we want to watch for ozone production. So the LED lamps are not. There is no risk of ozone production. I'm sorry. Yeah, ozone production, correct. Inside. Basically, we don't want to create more pollutants inside our homes. So what are our recommendations? The recommendations on basically the mechanisms are ventilation, 40 CFM per person. That's actually a number that you guys have heard in previous webinars. It's equivalent to reaching healthy levels of 800 parts per million of carbon dioxide. We also have air filtration. That's the recommendation is MERV 13 and higher. I explained hopefully why we want those higher designations. We want to have two filters, one for air recirculation, basically all the air that is inside our homes and recirculate through the HVAC system. We want to filter that one to remove the particles, but also all the fresh that is coming in. So everything that is outside might have some particles outside. We just want to get rid of them for that stream that is coming in. And then air purification, so micro activation with ultraviolet germicidal irradiation using the UV light without ozone production. And here is where we want to have a point. Is basically we just don't want to use only one mechanism to solve the indoor air quality. We want to use the three of them. Ventilation, we know that bringing fresh air will improve cognition, productivity, sleep. Air filtration is going to remove all these particles that might be very harmful. It creates respiratory and cardiovascular diseases. And then air purification, if there is a seasonal disease, we want to also minimize the probability of infection through basically microbe deactivation using UV lights. And that's basically what we want to, our story is basically how to reach this healthy and safe space is basically the combination of three, a balance of ventilation, air filtration, air purification. And it's proven basically having the three together. This is more the for ventilation. For filter is about 90% depending on the filter, and the ultraviolet for microbes 85%. And then if we combine those three, we could basically we could remove most of the basically 99% of the microbes as well. Now let's talk about smart systems. So now we know how to solve the root problem: monitoring, compare, and then act. And we now know that source control, ventilation, filtration, microbe deactivation. So we want to actually do it in a smart way. And what are the fundamentals of smart systems? So everything that we hear, we could do it manually. Basically, if I have a problem with bad air, I can open a window. But sometimes we just don't want to worry about it. Now we have a lot of technology affordably that we can reach. That they can do that for ourselves. So we can enjoy life without worrying about the indoor air quality. We have, so basically the fundamental of the smart systems is we have the input signal. Basically, what are the requirements? That would be the signal for the smart system. Then we have the control variable that is basically the indoor air quality monitors. And now there is the technology that is going to use a controller to generate the output, just understanding what are these electrical signals coming into this device. And this device is going to tell my HVAC system, my ventilation system, what to do and when to do it efficiently as well. And this is a closed loop. This is important because here is the feedback loop that we want. We want to monitor these indoor air qualities to be the most efficient we can. We want to ventilate when it's needed, where it's needed. Because life at home is dynamic. This is the typical monitoring in a house. Basically, this is actually located in a home. You see there are two people sleeping in a bedroom. They close the door when they are sleeping, and you see the levels basically in the night. They go to very high levels, and then they leave for work. So the levels are basically, when they are not there, they reduce the levels due to the infiltration and so on, but then go back and they start having these issues. And then now with the capability of monitoring, we can now understand and explain how to reach this indoor, a better, a healthier indoor air as well. And the smart, basically the smart ventilation, our recommendation is basically trying to bring down those levels with all these mechanisms: ventilation, filtration, microbe deactivation. So we have the control system that is going to monitor and then react. And this is where also real data where we're starting to see the impact of all these controls into indoor air quality. So we want to ventilate when it's needed. So and then use energy only when it's needed. One note about outside fresh air. So we assume sometimes that the outside air is fresh, and it's not always fresh. There is, depending on your location, you could have, basically there is a lot of pollution coming from the transportation, from industries, and now we're starting to see commonly wildfires that those particles could travel many, many, many miles and reach our homes. So the recommendations for this is basically filter the outside air coming to the building. MERV 13, as I mentioned before, effective. That's what we recommend. And using a smart system. So a smart system that is the ability to monitor and close the vents when high levels of pollution are outside. So definitely we want to monitor outside, and we want to understand, and if it's the levels are threatening, health threatening outside, we just close, and then we just keep the recirculation mode to filter and purify the indoor air. This is basically giving some more background on what you just said. It's basically, yeah, if we have particles outside of unhealthy levels of 50 micrograms per cubic meter, with an unventilated house, as I said previously, 2 to 5 times concentration levels indoors, we might have a really bad environment, worse environment than the outside. So if we do ventilation, that helps a lot. With some filtration, it will help us a lot. But if we combine ventilation and recirculation when it's needed, and depending on the sensoring, we could actually dramatically reduce the particulate matter inside the house with a smart system. And finally, sustainability and cost of health. So let's talk first about health statistics. And this is something that I just got. This is a 2022 statistics from the American. More than 4 in 10 Americans live in places with unhealthy levels of air pollution. That was the major finding of these statistics. And not only that, Americans is now, based on this study, the Americans are experiencing more days of very unhealthy and hazardous air quality than even before in a 2-decade story that they have been collecting data and analyzing. So when we design and renovating buildings, the top priority we need to focus is in healthy indoor air. We need to design to make sure that the indoor air is healthy. Now we know everything that I just mentioned is affordable, especially the monitoring systems. We want to include those systems in there. And limits is basically everything related to reducing energy, reducing carbon emissions. Is basically definitely we want to go that road. We want to reduce energy. We want to reduce carbon emissions. But these are basically limits. We want to put some limits on that. But it shouldn't be the priority. The top priority is basically understanding and achieving the healthiest indoor air. And one additional note, is basically about what are the paths. So there is many paths that to achieve zero energy buildings, basically reducing energy use, access to clean energy, and reducing carbon emissions. So we have quite a few. We have ASHRAE standards, we have the passive houses standards, and we also have the DOE. They have their own standards. Those of them, they are doing an exact, very good job trying to guide us on how to have a more sustainable home. One of the key parameters is trying to achieve this ultra tight enclosure, basically trying to reduce the infiltration that it's from our homes, minimizing infiltration. And now just this, it requires balanced mechanical ventilation. Let's remember, we need to bring fresh air. If we are minimizing infiltration, we want to also improve the ventilation through balance map. So all these paths are adopting this ASHRAE standard 62.2 as the ventilation standard. One caution that we are trying to communicate through these webinars is that the current version is not a healthy standard. There are important papers now that there is the capability of measuring, doing experiments with monitoring indoor air quality. The same papers are basically explaining that the current ASHRAE standards as it is, they are creating issues in health, cognition, and productivity. As I mentioned, go to the website to learn more about it. But basically, what and here what it says, it's acceptable because of the ventilation guidelines. It's creating this significant decline in many areas, in the cognitive function and so on. So, and why? So the question is why? So the current ASHRAE standards as it is, as today, is just based on dissatisfaction with respect to odor and sensory irritation. Basically, they were done for bathrooms and kitchens, basically trying to get rid of that to reduce the dissatisfaction for us. The standards as today, they are not monitoring pollutants. And through this webinar, we learned the importance of monitoring pollutants. And therefore, there are no guidelines on minimum pollutant allowed limits. So those are the things that I'm working with. We're basically trying to bring that into the attention with ASHRAE to make sure that now next generations of ASHRAE standards, they will start including that. And therefore, this is not based on a constant flow. Constant flow is basically odor-based. And the papers that we show that I showed previously, the coefficient values of this calculation. This is a formula that they use. This is the total required ventilation rate. This is the dwelling unit. This is basically the area of your home. So they put a factor here, and then they have another factor that is based on the number of bedrooms. Studies, the ones that I showed before, showing that those current coefficient values are creating sick building syndrome, cognitive function decline, productivity losses, and we know also that it will create some health problems. So, and as a Build Equinox, as a company, we have directly measured that. So this is real data. When there is insufficient ventilation, this is basically a home that is very efficient. It's basically certified passive house with a heat recovery ventilator, no recirculation, and using the ASHRAE standards. When it's occupied, the ventilation is insufficient. So we see all these high levels of carbon dioxide and VOCs when it's occupied. And when there is not occupied, actually it's excessive. So because it's constant ventilation. So for when it's unoccupied, actually it's overventilated. So, and we have done a lot of analysis on that. So this is an example, how the ASHRAE standard equation. This is for a 3-bedroom that is basically assuming that there is 4 people in this bedroom. The ASHRAE standard is basically aligned. As I mentioned, the higher the home, the higher the fresh air per person. So it looks like, and the graph looks like that. So what happens? Let's assume that the average home is about 2,500. So when we have a house that is 2,500 of home size, the fresh air is about 20 CFM per person. What happened with the carbon dioxide? At that level, the carbon dioxide of this home, 2,500, is about already 1,000, a little bit over 1,000. So that means that already, as an average, that home is already unhealthy. So what happens if these 4 people, or if there is a smaller home? So small homes are under-ventilated. So if it's a smaller home that 2,500 square foot with a 3-bedroom, 4 people, the carbon dioxide is way even worse than the one explaining before. But also large homes are now over-ventilated. So let's say a home that is about 4,500 square foot, there are a lot of waste of energy, over-ventilated. They don't need that much. Yes, especially, I'm talking about average here. There is no difference between sleeping and exercising occupants. Basically, there is no feedback loop on what is happening inside right now with the current ASHRAE standard 62.1. One of the questions that we always enter is, okay, now you guys are asking us to increase the ventilation, increase. So from the minimum standard is about 20 CFM, we want to increase it to 40 CFM, that's equivalent to 800 particles per minute. So what is going to happen? What is going to be the cost? We're going to definitely a lot of fan power. So we have done that, basically that research just to answer that question. So for a typical minimum standard, when the airflow is about 20 CFM per person, we have about 1,200 parts per million for concentration. When we increase, definitely when we increase we double the ventilation, the carbon concentration, carbon dioxide concentration is going to lower to 800. What is going to happen? Basically, the calculation based on typical outdoor, indoor. Here we are heating. We're in winter with no heat recovery. It's about 2 cents per hour per person. This one is analysis that we did with no heat recovery, constant flow all the time. So that's basically the cost that we need to add in order to increase the ventilation to healthy standards. So the question is, when you take a holistic view, improving ventilation that we know is going to reduce sick days, we're going to improve health, we need to have a holistic view where we need to do the calculation of cost of energy and include the cost of doctor visits and the cost of products. So if we put together the papers that I have pointed out, they give more detail. Definitely is going to reduce the overall cost, making your home more healthier by moving and reducing this carbon concentration to less than 800 parts per million. Energy recovery, another topic that it should have their own webinar. We use the energy now. Everything that I discussed here is basically constant flow, no heat recovery, and no energy recovery. So we're talking about 2 cents per hour per person. Now with energy recovery, that cost should be less. We want to use this energy. So energy recovery is basically use the energy from existing conditioned air from the building that is coming out to condition the fresh air that is coming to the building. We know that that will reduce the cooling or the heating load to condition the outside air, saving some energy. We have 3 major ways to do that. One is the heat recovery ventilator that only transfers heat, the energy recovery ventilator that transfers heat and humidity, and then we have our own, the technology that we use is actually a heat pump energy recovery. We use a heat pump just to transfer the heat and the energy between the 2 streams that they are coming out and coming in, and also provides additional conditioning and some dehumidification. Now, when we talk about smart systems, this is a good comparison. This is an infographic where I show this is a ventilation at constant flow. So we are using, the fan is always running. So the energy use is basically there. It's constantly spending some kilowatts per hour. When we use ventilation at constant flow with ERV, basically with an energy recovery, we're going to have some savings, energy cost savings due to that precondition of the air. But now if we use a smart ventilation with an ERV, we are measuring the indoor, when we are measuring indoor air pollutants and we ventilate when needed, now the energy savings is even more. So that's how we want to incorporate all these smart systems into the ventilation, trying to measure indoor air pollutants and ventilate when needed. Sorry, I think I extended a little bit too far. I wasn't watching the time, but I'm excited. But in summary, basically, we learn the type of indoor pollutants. We know that there is quite a few. The smaller the particles, the harder is for us as humans to get rid of. There are also gases contaminants that they might be, some of them are very harmful. There are some that are deadly. We want to watch for them. We know all the effects of human health. On human health. Especially, we are interested in the ones that they're making us sicker. We also learned today about particle deposition. The smaller the particle, the deeper it goes into the lungs, creating many health issues. It depends on concentration. This is always one we want to highlight. It depends on concentration levels, exposure time, age, and health conditions. And we want to solve the root problem. Basically, we want to monitor the pollutants. They're giving, now innovation is giving us affordable sensoring equipment to do that for us. We want to compare. So based on a lot of extensive research from Equinox, we're providing our own indoor air quality guidelines. And then we want to have a smart system to help us reduce these pollutant levels. We don't have a one solution to solve all. We want to use all of them as possible: source control, ventilation, filtration, microbe deactivation, and absorption. And we provided some numbers for the Equinox Healthy Indoor Air Quality Guidelines. Those numbers, some of them we are had a lot of years of research. Some of the numbers we are working on it as well. So we have some, yes, we will be telling you more about it in the future. But basically, it's all related on research and impact on cognition, health, sleep quality, and productivity. We know the mechanisms to reduce the pollutants. Today, I was focusing more on filtration because why filtration is effective for really small particles. And what is the smart ventilation? And that's actually the secret sauce that we have discussed and how we're developing new generation of smart ventilation systems, or is based on this webinar. Basically, today was the basics of indoor air quality and how to reach a healthy indoor air quality. Measure pollutants or systems measure carbon dioxide, VOCs, PMs, particulate matter. We use the Equinox Indoor Air Quality Guidelines, so we have that embedded in our controls. And we take action, not only ventilation, even though we call it a ventilation system, it does more than that. It does ventilation, filtration, microbe deactivation is optional, and also has the smart capability of learning on using 100% outdoor air or just keeping a recirculation as well. And we do it efficiently. We use smart controls, wireless communication, using all the innovation that is coming, that we have access, and we do it efficiently also with heat pump energy recovery. So I'm sorry we extended a little bit too much, but thank you so much for attending this webinar. Any questions? Please, maybe we have 5 minutes to answer any questions. Let's see.